If not, if everything is fine, then well, good. So, okay. Boolean algebra, this already we have done, so I won't be discussing this again. But I have kept this slide because we maybe at some point of discussion we may require to refer to all these theorems or some of these theorems. So that is why I have kept this slide as such. Now, this again is already done. So we were actually discussing this sum of product and product of sum form. And then we obtained that for this expression, sum of the product form was this one. And we used some theorems. We will be talking about that. And product of sum form comes out to be like this. So I have properly convinced you that what is the meaning of product of sum, because these are sums. This is product, so that is why this name product of sum. Here it is sum of products, means products being added to each other. That's called sum of products. So we try to see this, how we can actually realize this circuit. So if we stick to this expression simply as such, then how we will be able to get the truth, the final circuit corresponding to this. First term gives you something, suppose y1, a or bc. So this is nothing but bc. ORed with a gives you a or bc. Then second term b or c bar a. And last, then you have to AND these y1 and y2, giving you the final expression. But there is something important here to note, that okay, here this gate is in series with this gate. This AND gate is in series with this gate. Same is the case here. And this AND gate is in series with both of them. And what happens in any digital devices or in any digital circuit, that whenever you change the inputs at any one of the gate, there always is some delay for output to change. I'll be showing this in, not today, but in coming classes, why that delay comes. The delay comes because this device takes some time to reach an equilibrium state. Well, so in that case, this delay is introduced. So suppose you change some inputs here, so suppose both are 1 here, and then output will be 1. Now suppose you change one of the input from 1 to 0, output will go to 0, but not instantaneously. There will be a delay of few microseconds maybe, but yes, that is there. So this delay, what will that do? That will, more are the number of gates in series with each other, more will be the delay, because this gate will have its own delay. So all the gates in series, for gates in series, delay will add up, and for gates in parallel, there won't be addition of the delay. So if the gates are in parallel, then one set of gates, they may have similar delay time. Then other set of gates, which is in next step to this, they may have similar set of delay time. So parallel connection is not a problem, but series connection has a problem, that delay times add. So suppose you have a very long circuit, one AND gate, some NOT gate, OR gate, ye, wo, blah, blah. So suppose you have 10 set of gates in line, and final is the output. In that case, what will happen? The delay will be 10 times the delay of each stage or each level. So that is why, to avoid this delay, and that will make the processing of your device slow, because you have to change you have to keep a margin, so that okay, all that delay can be adjusted. Then and only you can change the input to the next level. Suppose you have to feed in some inputs to this gate, like 1 0 1 1 1 1 0 at B, suppose. Then you have to make sure that every change is registered at the output, isn't it? So for that, you have to keep the margin of the time, and that is what will make the operation of the digital circuit slower. So our objective is to reduce number of gates in series, of course, and try to look for alternate possibilities of the circuit for this expression. And that is where we will now illustrate applications of Boolean algebra, how Boolean algebra can be helpful in designing a simpler circuit with lesser delay time. Okay. So I hope you remember in yesterday's class, we had seen that this expression itself actually can be simplified to this sum of products form. This is sum of product form, but not canonical form. I hope you know what is canonical form. We have yesterday discussed. Today also we will follow up what is canonical form. But this is sum of product form. So this simplification, how this has been followed, I tried to put up the steps here a little much more detail. So this is so here you will see there are 4 terms. Here you will see only 3 terms where all other terms went. So there is some term called a c bar a here, right? So what we are doing here is, okay, we are writing it like a dot a into c bar. We can do that in Boolean algebra. This is nothing but a dot a is nothing but a, isn't it? A and a. You have done it earlier. That is nothing but a. So this becomes ac bar. Similarly, bcb, this one. BCB is again BC. Similarly, BCC complement A. So CC complement is nothing but 0. So this gives you 0. This term goes to 0. So ultimately, you arrive at this. So that's how Boolean algebra is really very helpful to quickly solve things and simplify things. Well, if you stick to this expression, then we can actually get this same expression realized in 2 level. That's why we reduced 1 level now. Earlier we had some AND gate, some OR gate, followed by another AND gate. We are ignoring no NOT gate as of now. So C bar means, but of course there has to be some NOT gate as well. So now that 3-level circuit now has been changed to a 2-level circuit. Here all the gates are in parallel. This is in series, but then delay time of such a implementation will be lesser. So these are all the practical aspects we have to keep in mind. So I hope you can see this is nothing but AB. Then this is nothing but AC complement. This term. This is BC. This term implemented here. All these are odd. That is why we call sum of products. So this part or this level takes care of product part. This level takes care of sum part. That is why sum of product implementation is a 2-level implementation. If you take any Boolean expression and somehow can express that in a sum of product form, then we can reduce that complicated circuit into a 2-level circuit. In 1 level, you will be in a position to write down the products, which may be done with the help of AND gates. And in 2nd level, we may use OR gate to take the sum. That is why sum of products. So this will reduce the delay time. I hope this is clear to you. So this is a simplification of the previous one. There was another thing which we did, that was a product of, there is another, let us stick to the same expression and try to see that can we simplify this further. Let us stick to this expression and see if we can simplify it further. So in this, how many gates are being used? 1, 2, 3, 4 gates. So of course, if you add cost to each gate, the cost will be, suppose each gate costs at the rate of X price, then the total cost of this circuit will be 4X. Now the question is, can we really simplify and do the job with the lesser number of gates? Don't know, but okay. Okay, this part don't answer that question, but this part try to answer the question. That is it possible to implement this gate, this expression using only NAND gates? Now one question is, can we implement this expression using only NAND gates? So here is the Boolean algebra to do that. Now, okay, what we do is we try to use this, we take this and take complement on both sides. Now, when we take complement on both sides, then we can apply De Morgan's theorems. So what will De Morgan's theorems say? I hope you know what are De Morgan's theorems. Yesterday we have done that. So, I mean, A or B, let us say this one, say X or Y or Z, whole not. What will that be? X naught, Y naught, Z naught, all ended. And I mean, or expression changed to and of expression. I hope you know that, you remember that. Then let us say this is y1, y2, y3. These all are y1, y2, y3. Then what we can say? Now this is y bar. This part is nothing but y bar. On right hand side is the expression for y bar. So if we want to write down y, let us say, okay, this is y1. Let us say this is y1. So what will be y finally? We have to take complement once again. So that will be equal to nothing but y1 dot y2 dot y3 whole complement. Now we won't apply De Morgan's theorem back to reach here. We leave the expression here. Why here? Because we have to implement the expression with the help of NAND gates. And what is the interesting part here is that this expression on right hand side is representing a NAND expression, and not, and followed by not, right? So that's an AND expression. So how we can implement this same expression using only NAND gates is this simple way. Because, okay, now this y1 in itself is a NAND expression, isn't it? A and B whole not. So this is NAND, this is y1. Similarly, y2 is NAND itself. You can see from here. This is y2. A C complement not. So A C complement whole not. That is now NAND gate. Again y3 BC not, BC not. So this is a level 1, 2-level circuit again. But now we are using or employing all the NAND gates to get the task done. And finally, y1, y2, y3 are NANDed to each other. I mean, using a NAND gate, another NAND gate, we can get y. This circuit will also do exactly the same task as that of the previous case. I mean, this circuit and this circuit will do the same job. The only difference is that one uses only NAND gates, other uses combination of AND plus OR gate. I hope this is clear. Is this okay, or is there any question from this part? Is this clear to everyone? Any question from anyone? Okay. Okay, meanwhile, you also sign your attendance. Well, so next, okay, then there is a question. Okay, can we do the same job with the help of NOR gates only? Now, okay, you try to see this one. Try to use some common sense. Try to use your own mind, and try to see if we can. This was sum of products. If you have to obtain NAND implementation, you have to begin from SOP and then do something like this. If you have to go to NOR operation, means you have to implement everything using NOR gates. Then what you do is you go to product of some expression and then do similar things. And then again you have to use De Morgan's theorems. Let's try how. So now this will be giving us the implementation in terms of NOR gates. How? We take a product of sums. This is product of sums. We had done it yesterday. Do complement of both sides. Now this, again use here De Morgan's theorem. De Morgan's theorem says, okay, A, this is a y1 and y2 and y3 whole bar will be y1 or y2 or y1 bar or y2 bar or y3 bar. So OR operation, right? So this is how you can write it down. Now ya is A or B. You again complemented it. So y, ultimately we need y, not y complement. So that is why we complemented it again. Now this form leads you to a NOR gate based implementation of the same circuit. Can you see the circuit? Can you draw the circuit? This would look like this. I hope you can see how product of sum form can be obtained to get NOR equivalent of any Boolean expression. So by this time you should somehow have got significance of the sum of products or product of sums form. So these forms are helpful in reducing the level. I mean, from a 3-level or multi-level Boolean expression, we can get a 2-level Boolean expression. We can also arrive at a NAND or NOR implementation of any Boolean expression. That's another interesting thing here. And well, we can compare the two. That this was a previous implementation using OR gate and AND gate. This is using only NOR gates. Okay, so that is how this what you call Boolean algebra or the theorems of Boolean algebra are actually helpful in arriving at various possibilities of circuit design. So the same expression now we have seen can be implemented in various number of ways. So now that is where efficiency of circuit designing is important, that you should actually be in a position to obtain simpler circuit with fewer components doing the same job. Okay, now there is a question that can we really go to the fewer components? Can we reduce number of logic gates? Yes, this is that sum of products expression for this y, same. This is represented by this. Now this can be simplified to obtain this. Now you will ask how? So here we have used one of the theorems of Boolean algebra, theorem 1.19, which says that, okay, if we have AB or A complement C or BC, then that is actually equal to AB or A complement C. Now here the things have been changed a little. Here it is C complement, here it is A complement. Here it is BC, BC are same. AB, that is all same. So instead of C complement, here is A complement. Instead of A, here is C. You can equate the variable or find out the corresponding variable, and then final expression we can obtain will actually be BC or AC bar, right? So this very simplified form will reduce the number of gates. Anyhow, is there other way of doing so? Yes, there is another way as well. We start with the product of some expression and then apply another theorem, the theorem which is, I mean, we can say complementary to this one, where each AND is replaced with OR and so on. And then if you apply, you will be able to actually get that this is nothing but equal to this one. So that is why those theorems of Boolean algebra should be, I mean, in your mind, and you should be in a good position to apply them as per the situation requirement. Now, what is the simplification? If you look at this one, this can be obtained using NAND gates, BC, okay, then AC complement. Oh, then you will say why this should be a AND gate, not a NAND gate. And then 2 should be ORed, right? This is BC or AC complement. But here again, we have employed indirectly, actually, we have indirectly employed De Morgan's theorem. Because this this is a NOT gate, this is a NOT gate, right? This is an AND gate. So A naught and B naught is actually equal to A or B whole naught. I hope you remember this. Let me show you in the first slide which expression I am talking about. Oh, that's not De Morgan's theorem. Ah, yeah, this one. So there, we have to get actually what we have is NAND gate. So we have one expression, other expression. Finally, what we will get A or B whole bar. So these two are equivalent. I mean, this one. Sorry. Yes. So this will lead you to the same expression. Okay. I hope you are able to do this. Are you comfortable with this? Can we arrive from? Okay. I give it to you as a quick practice right now. You try to arrive from here to this one, and then prove that y actually is equal to BC or AC complement. Use all theorems of Boolean algebra which you can use, and then you have to arrive at this point. Let me know how many of you are able to do this. Yes, the Benchy says she can. What about others? Yes, others, are you able to get y is equal to BC or AC complement? Jyoti is getting it. I hope if you are writing yes means you have done it. Okay, be honest. If you're not getting, you just let me know. I can help you. Okay. Others, very good. Anshika. Anshika is getting it. And others, yes. Anshul, Subhash, Shubh, Abhi. Okay. So you should be actually able to get this. Okay. Similarly, if we have to, so now interesting thing is that our earlier NAND implementation was using 4 NAND gates. So what we obtained here is that now we can implement the same expression using only 3 NAND gates. Even if you try using NOR gates, you can get the same expression, and it can actually be done with the help of only 3 NOR gates. So that's the importance of Boolean algebra, that we can design circuits in various possible ways. Fine. So we were yesterday talking of something called min term and max term. So, I mean, we noticed that these equations, actually 5.3 and 5.5 means he is referring to these two equations. This one, which is product of sums, and this one, which is sum of products. What he's saying is that these two forms are not in canonical form. Why? Because each term in these, we had discussed this yesterday itself, that each term doesn't contain all the literals. I hope you know now what are literals. All terms doesn't have all the literals. Therefore, that is not a canonical form. Okay. However, in case we could put them in canonical form, then each term will be termed as min term in case of SOP and max term in case of POS. Now, usefulness of min term and max term is going to be clear shortly. I'll be demonstrating it in coming lectures and even some part of it today. But yes, why we need to go for canonical form and why to look for min term, max term is something important. So we will be looking at this now. So if SOP form is not in canonical form, how can we convert it to corresponding canonical form? So basically we take SOP form, sum of product form, and then we can get corresponding canonical SOP form. So there are two things. One is SOP form, sum of product form, and second is canonical SOP form. So this form, sorry, yes, this form is SOP, sum of products, but not, this is not canonical SOP. So there can be SOP, there can be canonical SOP. Note it carefully, okay? So you take any SOP form, and then you don't, suppose this is not in canonical form. Then what you do is actually by ending the terms in the expression with the term formed by ORing the variables and its complements which are not present in the term. Now this language may be a little confusing to you. We will do it as a practice, then things will be clear. For example, suppose we have a 3 variable expression with variable a, b, c. Suppose there is some expression in which there are 3 variables a, b, and c. And if there is a term a in that expression, then means b and c are absent. They are not present there. Means all literals are not present. There is one single term. Suppose a, something like a or bc. Okay. So then how to make this canonical? So a or bc is a sum of products form, right? Bc and a. But then suppose a is not a canonical term, right? So how to get canonical form? Then what we do is that to this term, which is a, b and c are not existing. So what we do is we take b or b bar and c or c bar, and then this is what we're doing. So a and b or b bar and c or c bar. Oh, let's not pay attention on this one which appeared. So a and b or b. So in this term, the literals of which variable are missing. What you will do, you will take that variable and or that variable with its complement. So what will this be? 1. You know, b or b bar is 1. So that doesn't affect things at all. Similarly, c or c bar is also 1. So a and 1 and 1. That's what we are doing actually. But we are trying to incorporate b and c here. So what will this be? Then we can use the theorems of Boolean algebra and get corresponding canonical form. So a simple term a will have canonical SOP form given by this one. So each term here, it has a, b, and c, all 3 literals. A, b complement c. So b is also present here in its complement form. So that's also a literal. So this is how we can obtain canonical sum of product form corresponding to some variable. Let's practice it. It won't come as such. Let us take this expression now. This is a sum of products for the given expression which we were following. Now we have to obtain sum of products form of this. So what we see in first term, C is missing. In second term, B is missing. Third term, A is missing. So first term, C is missing. So what we will do, we will take C or C bar and that to this expression. So that's what we have done. So in first term, C was missing. So we did this. Second term, B was missing. So we did this. Third term, A was missing. So we did this. So overall, we did nothing. Everything is exactly the same way. We just incorporated the variable. Then we multiply. We get ABC or ABC complement. 2 terms from this. ABC complement from here. AB complement C complement. BC ABC, one and same thing. A complement BC. So Boolean algebra is applied. Now I leave it as a homework for you. You try to see that, okay, which theorem has been applied to actually arrive. This has 1, 2, 3, 4, 5, 6 terms. But now we have only 4 terms here. So any 2 terms has gone. Which one and why? That you try. So you can even pay attention that, okay, which all is present here? A, B, C complement. These 2 are present as such. Now here is A, B, C complement. And then AC complement. You can take AC complement, AC complement common, then you will have B or B complement. No, we can't do that because that will be the same thing. Okay, so you have to make sure that all terms retain all literals. So, okay, just a minute. Huh? A, B complement, C complement. So this term is here, A, B complement, C complement. This term is this one. This term is this one, isn't it? This term is this one. I hope you can follow my cursor, right? And this term is this one. Now these two terms, ABC, ABC, exactly same. So we have done in Boolean algebra. A or A is A itself. So that's ABC. There must be other two terms which are same. ABC complement, ABC complement. So they led to the same term. So that's how we arrived at this, which is nothing but sum of product of this expression in canonical form. So what all literal, what all, so all these terms are called min term. Each term in canonical SOP form is called min term. So this is a min term, this is a min term, this is a min term, this is a min term. I hope this is clear. Is this part clear or any question? Yes, please. Is min term clear? How to obtain from non-canonical SOP to a canonical SOP form? Is this okay? Any query? Okay, no query. Very good. Now let us take another form. Now this is POS. This is product of sum. But this is also not in canonical form. So now how to obtain from here the canonical product of some form? Notice here what we did. This was AND. So we did OR here. Here is opposite. Here is OR. So we have to do AND. How to do AND? Whichever variable is missing, we have to do what we have to do. Okay, let us try it here. So now you have A or B. Now we did OR CC complement. What is CC complement? Is 0. C was absent, so we did CC complement. This is 0. So if you OR 0 to anything, nothing changed. Same is the case here. Here B is absent. So we did B complement. This is also 0. So no effect. Here we did A complement. Simplified things, simplified further, and obtained the canonical product of some form. Right? So now you can see that each term has all three literals, A, B, C. So this POS form is canonical product of some form. Is this clear again? Or is there any confusion on this? Any question? Okay, I hope it is fine. So that is how we can obtain from any form, canonical form. Okay. Do practice them properly. You may see a lot of questions in your exams from this. Well, the concept of this, so the question is, why is this min term and max term so important? So actually the concept of min term and max term is very, very important in a sense that it will become convenient to represent our basic logical expressions in terms of min term and max term. It will be clear shortly. Before I do that, let us move to the next slide. Okay, here is a 4 variable. Suppose there is some Boolean expression or some digital circuit which has 4 inputs. So how will the corresponding Boolean expression for such set of 4 variable be written? So we actually, if you have to write down, say, product of some form or sum of products, or product of sum, we employ min terms. So How we employ min terms? So these are the combinations. A, B, C, D, 0, 0, 0. This is like counting, binary counting, weight numbers. 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, and so on. And corresponding min term, how we write down? Mini term. That's called mini term. Okay, sorry. Mini term is like, okay, if all are 0, we write it like A complement, B complement, C complement, D complement. And that mini term is called M naught. If D is 1 here, only D is 1. So D is written like this. So we write down mini term in such a way that they come finally like 1, 1, 1, 1. Okay. So if inputs are 0, 0, 0, what will be 0 complement? 1. So that is why I wrote here A complement, not A. What should be B complement? 1. So that is why we wrote B complement here. In this case, A, B, C all are 0. So we wrote A complement, B complement, C complement. D is already 1, so we don't need to take its complement. So D. That's the way to define this. I mean, this is just a convention or something interesting which will be clear shortly. So this is a mini term called M1. So, but something worth noting here is that M1 means this only. M2 means 2. This is 2. In binary number 4-bit system, this is 2. So you call it M2. If you have to write down mini term corresponding to M2, that will be, now you have to see the combination here. A bar, B bar, C, D bar. A bar, B bar, C, D bar. If you have to write down term corresponding to 8, M8, mini term corresponding to 8, M8. So that will be A, B complement, C complement, D complement. Some similarly M13. M13 will be A, B, C complement, D. Is this clear? Mini term, how to write down mini term, and what is the significance of mini term for a 4-variable system? Is this okay? We will be using them, but okay, first let's understand mini term as such. What is a mini term? Is this okay? All right. Similarly, if you are employing product of sum, then we will use max terms. Rule is opposite here. Now note things carefully. In case of mini term, you will be using complements. Means to make one, we will be using A complement, B complement accordingly. But in max term, if these are 0, we will write down the variables as such, A or B or C or D. Here D is 1, so we wrote D complement. Here C is the 1, so C complement, and so on. That's how we can write down max term. So if somebody asks you that you have been given a 3-variable set, write down all the mini terms and max terms. So you should be in a position to write down all the mini terms and max terms. In a notation, mini terms are like small m1, sorry, m0, m1, m2, m3, m4, and so on up to, you will go in case of 3 input variable, you will go up to m7, isn't it? M7, and what will be the M7 in case of 3 variables? It will be, what will be the mini term M7? This will be ABC, okay? And max term for same thing for say M7, capital M7 will be A complement, B complement, C complement, A complement or B complement or C complement. I hope this is clear. Huh? Well, so now let us try to see the usage of these min term and max term. So that's what I told you. This first paragraph, this part talks about all this table, which I told you directly. Now, similar to min terms, the max term is represented by capital MI. I is the corresponding decimal equivalent. I told you already that also. Fine. Now, what he's saying is, okay, using these notations, SOP 5.9. Okay, let me show you which is 5.9. Basically, 5.9 is this canonical form. Okay, let me write it for you. Just hold on. Okay, 5.9. Yeah, just a moment. Just a sec. This is your 5.9. Okay. So this is like y is equal to this. So this is y is equal to. Now you in your notebook write down all the full table for 3 variable min terms. You write down table for 3 variable min term. So you will be like m naught. What is m naught? Small m naught. What is m1, m2, m3? Write down all of them in the table. So m naught will be a bar, b bar, c bar. M1 will be a bar, b bar, c. M3 will be a bar. What will be M3? Yes. Okay, you define things like this. Okay, M naught. You define in chat box it like this. M naught is equal to ABC. Sorry, M naught is equal to A bar. We will write down A bar like this. Okay, BA, BB, BC. This means A bar, B bar, C bar. Okay, M1 will be equal to small b means A bar. Okay, A bar, B bar, C. M2 will be equal to what? A bar, B, C bar. Are you getting what I am saying? What will be M3? M3 will be equal to A bar, BC, I think. That's how you can write down, right? What will be A4? Write down all these terms. Yes, very good. M2 is B if written before a variable means that bar, variable bar. You are not getting the notation maybe. Others, 2B cannot be right. Capital B or capital A or capital C means variable name. Okay. And small b represents the bar. So if you write down BA, that means A bar. If you write down small bb, that means B bar. Okay. So I mean what is C small c? There will be nothing like small c. Small b only is used to represent the bar. So I hope you have a sufficient common sense to take care of this. Pranjal, whenever we are writing min terms, they are written with small m. When we are writing max term, they are written with capital M. So follow the rules accordingly, okay? So now, okay, I mean, I hope you have written it in your notebooks as well. It will be easy for you to write it in your notebook. So let me also write down on my rough paper quickly. So 0, 0, 0, that is M naught. This is A bar, B bar, C bar. You all, those who have not written, do write it in your notebook. Meanwhile, I am also writing it in my, what you call, rough paper. M1 will be 0, 0, 1, which is A bar, B bar, C. M2 is 0, 1, 0. A bar, B, C bar. M3 is equal to 0, 1, 1. A bar, B, C. I hope, yes. M4 is equal to 1, 0, 0. So A, B bar, C bar. M5 is 1, 0, 1. A, B bar, C. M6 is 1, 1, 0. A, B, C bar. M7 is 1, 1, 1, which is A, B, C. Okay. Now follow this expression. Y. How can we write down Y in terms of min terms or product of sum equation? Sorry, sum of product equation. We can write down that like M3. Now you follow. What is M3? M3 is A bar BC. Can you see this one? This term is representing M3. Similarly, you have M4 here in this expression, which is nothing but A, B bar, C bar, this one. Okay. Similarly, you have M6, not M5. So M6 is A, B, C bar, A, B, C bar. And we have M7 as well, A, B, C. So by using canonical form of SOP or POS form or POS equation, we can write down any Boolean expression in terms of this kind of shorthand notation. So this can be written like, okay, y is equal to summation over m. Small m means min term, okay? So what does this mean actually? This means m3. So in bracket, we write only those values which are appearing here. So m3 plus m4 plus m6 plus m7. That's what is the meaning. So this expression, rather than writing this long expression, we can write down this short expression. So this is how min terms can be used to write down the corresponding SOP. Similarly, you can use max terms to write down POS. I hope it's here. No, it's not here. Okay, fine. Now I leave it as a homework to you. You take this POS. Okay, let's not do it as a homework, but keep it as such here. Let's do it just now. Oh, we have time, I think. No, we don't have time. It's 12:59. So I leave it to you as a homework. You come with this done as a homework for tomorrow. How we can write down this same POS form in terms of max terms. So in that case, it will be y equals capital M, whatever is this. This one is actually, you can see here, A, B, C. So one form, I'm sure, this is M naught. This is M naught plus, no, it's not plus now. In this case, we will write down M naught dot blah, 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 whatever terms are appearing here. Okay. So that is where these min term and max terms are useful. In next class, we will be studying more usages of these min terms and max terms. I hope that's clear. If there are any questions, I will be happy to answer. Yes, please. Are there any questions further? You have any doubts? Anyone? Okay, if there are no questions, well, thank you very much. Hope this was useful.